Section 62 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 5, of Electro-Chemistry, Part 2. A few years before, a philosophical institution had been established in London, under the auspices of Count Rumford, which had received the name of the Royal Institution. Lectures on chemistry and natural philosophy were delivered in this institution, a laboratory was provided, and a library established. The first professor appointed to this institution, Dr. Garnet, had been induced, in consequence of some disagreement between him and Count Rumford, to throw up his situation. Many candidates started for it, but Davy, in consequence of the celebrity which he had acquired by his researches, or perhaps by the intoxicating effects of protoxide of azote, which he had discovered, was, fortunately for the institution and for the reputation of England, preferred to them all. He was appointed Professor of Chemistry, and Dr. Thomas Young Professor of Natural Philosophy, in the year 1801. Davy, either from the more popular nature of his subject, or from his greater oratorical powers, became at once a popular lecturer, and always lectured to a crowded room, while Dr. Young, though both a profound and clear lecturer, could scarcely command an audience of a dozen. It was here that Davy laboured with unwearied industry during 11 years, and acquired by his discoveries the highest reputation of any chemist in Europe. In 1811 he was knighted, and soon after married Mrs. Apreece, a widow lady, daughter of Mr. Kerr, who had been secretary to Lord Rodney and had made a fortune in the West Indies. He was soon after created a baronet. About this time he resigned his situation as Professor of Chemistry in the Royal Institution, and went to the Continent. He remained for some years in France and Italy. In the year 1821, when Sir Joseph Banks died, a very considerable number of the Fellows offered their votes to Dr. Wollaston, but he declined standing as a candidate for the President's chair. Sir Humphrey Davy, on the other hand, was anxious to obtain that honourable situation, and was, accordingly, elected President by a very great majority of votes on the 30th of November, 1821. This honourable situation he filled about 7 years, but his health declining, he was induced to resign in 1828, and to go to Italy. Here he continued till 1829, when, feeling himself getting worse, and wishing to draw his last breath in his own country, he began to turn his way homewards. But at Geneva he felt himself so ill that he was unable to proceed further. Here he took to his bed, and here he died on the 29th of May, 1829. It was his celebrated paper on some chemical agencies of electricity, inserted in the Philosophical Transactions for 1807, that laid the foundation of the high reputation which he so deservedly acquired. I consider this paper not merely as the best of all his own productions, but as the finest and completest specimen of inductive reasoning which appeared during the age in which he lived. It had been already observed that when 2 platinum wires from the 2 poles of a galvanic pile are plunged each into a vessel of water, and the 2 vessels united by means of wet asbestos, or any other conducting substance, an acid appeared round the positive wire, and an alkali round the negative wire. The alkali was said by some to be soda, by others to be ammonia. The acid was variously stated to be nitric acid, muriatic acid, or even chlorine. Davy demonstrated by decisive experiments that in all cases the acid and alkali are derived from the decomposition of some salt, contained either in the water or in the vessel containing the water. Most commonly, the salt decomposed is common salt, because it exists in water and in agate, basalt, and various other stony bodies, which he employed as vessels. When the same agate cup was used in successive experiments, the quantity of acid and alkali evolved diminished each time, and at last no appreciable quantity could be perceived. When glass vessels were used, soda was disengaged at the expense of the glass, which was sensibly corroded. When the water into which the wires were dipped was perfectly pure, and when the vessel containing it was free from every trace of saline matter, no acid or alkali made its appearance, and nothing was evolved except the constituents of water, namely oxygen and hydrogen, the oxygen appearing round the positive wire, and the hydrogen round the negative wire. When a salt was put into the vessel in which the positive wire dipped, the vessel into which the negative wire dipped being filled with pure water, and the two vessels being united by means of a slip of moistened asbestos, the acid of the salt made its appearance round the positive wire, and the alkali round the negative wire, before it could be detected in the intermediate space. But if an intermediate vessel, containing a substance for which the alkali has a strong affinity, be placed between these two vessels, the whole being united by means of slips of asbestos, then great part, or even the whole of the alkali, was stopped in this intermediate vessel. Thus, if the salt was nitrate of barytes, and sulphuric acid was placed in the intermediate vessel, much sulphate of barytes was deposited in the intermediate vessel, and very little or even no barytes made its appearance round the negative wire. Upon this subject a most minute, extensive, and satisfactory series of experiments was made by Davy, leaving no doubt whatever of the accuracy of the fact. The conclusions which he drew from these experiments are, that all substances which have a chemical affinity for each other are in different states of electricity, and that the degree of affinity is proportional to the intensity of these opposite states. When such a compound body is placed in contact with the poles of a galvanic battery, the positive pole attracts the constituent, which is negative, and repels the positive. The negative acts in the opposite way, attracting the positive constituent and repelling the negative. The more powerful the battery, the greater is the force of these attractions and repulsions. We may, therefore, by increasing the energy of a battery sufficiently, enable it to decompose any compound whatever, the negative constituent being attracted by the positive pole, and the positive constituent by the negative pole. Oxygen, chlorine, bromine, iodine, cyanogen, and acids are negative bodies, for they always appear round the positive pole of the battery, and are therefore attracted to it, while hydrogen, azote, carbon, selenium, metals, alkalis, earths, and oxide bases are deposited round the negative pole, and consequently are positive. According to this view of the subject, chemical affinity is merely a case of the attractions exerted by bodies in different states of electricity. Volta first broached the idea that every body possesses naturally a certain state of electricity. Davy went a step further, and concluded that the attractions which exist between the atoms of different bodies are merely the consequence of these different states of electricity. The proof of this opinion is founded on the fact that if we present to a compound sufficiently strong electrical poles, it will be separated into its constituents, and one of these constituents will invariably make its way to the positive, and the other to the negative pole. Now bodies in a state of electrical excitement always attract those that are in the opposite state. If electricity be considered as consisting of two distinct fluids, which attract each other with a force inversely as the square of the distance, while the particles of each fluid repel each other with a force varying according to the same law, then we must conclude that the atoms of each body are covered externally with a coating of some one electric fluid to a greater or smaller extent. Oxygen and the other supporters of combustion are covered with a coating of negative electricity, while hydrogen, carbon, and the metals are covered with a coating of positive electricity. What is the cause of the adherence of the electricity to these atoms? We cannot explain. It is not owing to an attraction similar to gravitation, for electricity never penetrates into the interior of bodies, but spreads itself only on the surface, and the quantity of it which can accumulate is not proportional to the quantity of matter, but to the extent of surface. But whatever be the cause, the adherence is strong and seemingly cannot be overcome. If we were to suppose an atom of any body, of oxygen for example, to remain uncombined with any other body, but surrounded by electricity, it is obvious that the coating of negative electricity on its surface would be gradually neutralized by its attracting and combining with positive electricity. But let us suppose an atom of oxygen and an atom of hydrogen to be united together. It is obvious that the positive electricity of the one atom would powerfully attract the negative electricity of the other, and vice versa. And if these respective electricities cannot leave the atoms, the two atoms will remain firmly united, and the opposite electrical intensities will in some measure neutralize each other, and thus prevent them from being neutralized by electricity from any other quarter. But a current of the opposite electricities passing through such a compound might neutralize the electricity in each, and, thus putting an end to their attractions, occasion decomposition. Such is a very imperfect outline of the electrical theory of affinity first proposed by Davy to account for the decompositions produced by electricity. It has been universally adopted by chemists, and some progress has been made in explaining and accounting for the different phenomena. It would be improper, in a work of this kind, to enter further into the subject. Those who are interested in such discussions will find a good deal of information in the first volume of Berzelius's Treatise on Chemistry, in the introduction to the Traité de Chimie appliquée aux Arts by Dumas, or in the introduction to my System of Chemistry, at present in the press. Davy having thus got possession of an engine, by means of which the compounds, whose constituents adhered to each other might be separated, immediately applied it to the decomposition of potash and soda, bodies which were admitted to be compounds, though all attempts to analyze them had hitherto failed. His attempt was successful. When a platinum wire from the negative pole of a strong battery in full action was applied to a lump of potash slightly moistened, and lying on a platinum tray attached to the positive pole of the battery, small globules of a white metal soon appeared at its extremity. This white metal he speedily proved to be the basis of potash. He gave it the name of potassium, and very soon proved that potash is a compound of 5 parts by weight of this metal and 1 part of oxygen. Potash, then, is a metallic oxide. He proved soon after that soda is a compound of oxygen and another white metal, to which he gave the name of sodium. Lime is a compound of calcium and oxygen, magnesia of magnesium and oxygen, barytes of barium and oxygen, and strontian of strontium and oxygen. In short, the fixed alkalis and alkaline earths are metallic oxides. When lithia was afterwards discovered by Arfvedson, Davy succeeded in decomposing it also by the galvanic battery, and resolving it into oxygen and a white metal, to which the name of lithium was given. Davy did not succeed so well in decomposing alumina, glucina, yttria, and zirconia by the galvanic battery. They were not sufficiently good conductors of electricity, but nobody entertained any doubt that they also were metallic oxides. They have been all at length decomposed, and their bases obtained by the joint action of chlorine and potassium, and it has been demonstrated that they also are metallic oxides. Thus it has been ascertained, in consequence of Davy's original discovery of the powers of the galvanic battery, that all the bases formerly distinguished into the 4 classes of alkalis, alkaline earths, earths proper, and metallic oxides, belong in fact only to one class, and are all metallic oxides. Important as these discoveries are, and sufficient as they would have been to immortalize the author of them, they are not the only ones for which we are indebted to Sir Humphry Davy. His experiments on chlorine are not less interesting or less important in their consequences. I have already mentioned in a former chapter that Berthollet made a set of experiments on chlorine, from which he had drawn as a conclusion that it is a compound of oxygen and muriatic acid, in consequence of which it got the name of oxymuriatic acid. This opinion of Berthollet had been universally adopted by chemists, and admitted by them as a fundamental principle, till Gay-Lussac and Thénard endeavoured, unsuccessfully, to decompose this gas, or to resolve it into muriatic acid and chlorine. They showed in the clearest manner that such a resolution was impossible, and that no direct evidence could be adduced to prove that oxygen was one of its constituents. The conclusion to which they came was, that muriatic acid gas contained water as an essential constituent, and they succeeded by this hypothesis in accounting for all the different phenomena which they had observed. They even made an experiment to determine the quantity of water thus combined. They passed muriatic acid through hot litharge, protoxide of lead. Muriate of lead was formed, and abundance of water made its appearance and was collected. They did not attempt to determine the proportions, but we can now easily calculate the quantity of water which would be deposited when a given weight of muriatic acid gas is absorbed by a given weight of litharge. Suppose we have 14 parts of oxide of lead. To convert it into muriate of lead, 4 625,000 parts, by weight, of muriatic acid would be necessary, and during the formation of the muriate of lead, there would be deposited 1 125,000 parts of water, so that from this experiment it might be concluded that about 1/4 of the weight of muriatic acid gas is water. The very curious and important facts respecting chlorine and muriatic acid gas which they had ascertained were made known by Gay-Lussac and Thénard to the Institute on the 27th of February 1809. And an abstract of them was published in the 2nd volume of the Mémoires d'Archéie. There can be little doubt that it was in consequence of these curious and important experiments of the French chemists that Davy's attention was again turned to muriatic acid gas. He had already, in 1808, shown that when potassium is heated in muriatic acid gas, muriate of potash is formed, and a quantity of hydrogen gas evolved, amounting to more than 1/3 of the muriatic acid gas employed. And he had shown that in no case can muriatic acid be obtained from chlorine unless water or its elements be present. This last conclusion had been amply confirmed by the new investigations of Gay-Lussac and Thénard. In 1810 Davy again resumed the examination of the subject, and in July of that year read a paper to the Royal Society to prove that chlorine is a simple substance, and that muriatic acid is a compound of chlorine and hydrogen. This was introducing an alteration in chemical theory of the same kind, and nearly as important, as was introduced by Lavoisier with respect to the action of oxygen in the processes of combustion and calcination. It had been previously supposed that sulfur, phosphorus, charcoal, and metals were compounds, one of the constituents of which was phlogiston, and the other the acids or oxides which remained after the combustion or calcination had taken place. Lavoisier showed that the sulfur, phosphorus, charcoal, and metals were simple substances, and that the acids or calces formed were compounds of these simple bodies and oxygen. In like manner, Davy showed that chlorine, instead of being a compound of muriatic acid and oxygen, was, in fact, a simple substance, and muriatic acid a compound of chlorine and hydrogen. This new doctrine immediately overturned the Lavoisierian hypothesis respecting oxygen as the acidifying principle, and altered all the previously received notions respecting the muriates. What had been called muriates were, in fact, combinations of chlorine with the combustible or metal, and were analogous to oxides. Thus, when muriatic acid gas was made to act upon hot litharge, a double decomposition took place. The chlorine united to the lead, while the hydrogen of the muriatic acid united with the oxygen of the litharge, and formed water. Hence the reason of the appearance of water in this case, and hence it was obvious that what had been called muriate of lead was, in reality, a compound of chlorine and metallic lead. It ought, therefore, to be called, not muriate of lead, but chloride of lead. It was not likely that this new opinion of Davy should be adopted by chemists in general, without a struggle to support the old opinions. But the feebleness of the controversy which ensued affords a striking proof how much chemistry had advanced since the days of Lavoisier, and how free from prejudices chemists had become. One would have expected that the French chemists would have made the greatest resistance to the admission of these new opinions, because they had a direct tendency to diminish the reputation of two of their most eminent chemists, Lavoisier and Berthollet. But the fact was not so. The French chemists showed a degree of candor and liberality which redounds highly to their credit. Berthollet did not enter at all into the controversy. Gay-Lussac and Thénard, in their Recherches physico-chimiques, published in 1811, state their reasons for preferring the old hypothesis to the new, but with great modesty and fairness, and, within less than a year after, they both adopted the opinion of Davy, that chlorine is a simple substance, and muriatic acid a compound of hydrogen and chlorine. End of section 62. Section 63 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 5, of Electro-Chemistry, Part 3. The only opponents to the new doctrine who appeared against it were Dr. John Murray of Edinburgh and Professor Berzelius of Stockholm. Dr. Murray was a man of excellent abilities and a very zealous cultivator of chemistry. But his health had been always very delicate, which had prevented him from dedicating so much of his time to experimenting as he otherwise would have been inclined to do. The only experimental investigations into which he entered was the analysis of some mineral waters, His powers of elocution were great. He was, in consequence, a popular and very useful lecturer. He published animadversions upon the new doctrine respecting chlorine in Nicholson's journal, and his observations were answered by Dr. John Davy. Dr. John Davy was the brother of Sir Humphrey, and had shown, by his paper on fluoric acid and on the chlorides, that he possessed the same dexterity and the same powers of inductive reasoning which had given so much celebrity to his brother. The controversy between him and Dr. Murray was carried on for some time, with much spirit and ingenuity on both sides, and was productive of some advantage to the science of chemistry, by the discovery of phosgene gas or chlorocarbonic acid, which was made by Dr. Davy. It is needless to say to what side the victory fell. The whole chemical world has for several years unanimously adopted the theory of Davy, showing sufficiently the opinion entertained respecting the arguments advanced by either party. Berzelius supported the old opinion respecting the compound nature of chlorine, in a paper which he published in the Annals of Philosophy. No person thought it worth while to answer his arguments, though Sir Humphrey Davy made a few animadversions upon one or two of his experiments. The discovery of iodine, which took place almost immediately after, afforded so close an analogy with chlorine, and the nature of the compounds which it forms was so obvious and so well made out, that chemists were immediately satisfied, and they furnish so satisfactory an answer to all the objections of Berzelius, that I am not aware of any person, either in Great Britain or in France, who adopted his opinions. I have not the same means of knowing the impression which his paper made upon the chemists of Germany and Sweden. Berzelius continued for several years a very zealous opponent to the new doctrine, that chlorine is a simple substance. But he became, at last, satisfied of the futility of his own objections, and the inaccuracy of his reasoning. About the year 1820 he embraced the opinion of Davy, and is now one of its most zealous defenders. Dr. Murray has been dead for many years, and Berzelius has renounced his notion that muriatic acid is a compound of oxygen and an unknown combustible basis. We may say then, I believe with justice, that at present all the chemical world adopts the notion that chlorine is a simple substance, and muriatic acid a compound of chlorine and hydrogen. The recent discovery of bromine by Bellard has added another strong analogy in favor of Davy's theory, as has likewise the discovery by Gay-Lussac respecting prussic acid. At present, then, not reckoning sulphuretted and telluretted hydrogen gas, we are acquainted with 4 acids which contain no oxygen, but are compounds of hydrogen with another negative body. These are muriatic acid, composed of chlorine and hydrogen; hydriodic acid, composed of iodine and hydrogen; hydrobromic acid, composed of bromine and hydrogen; prussic acid, composed of cyanogen and hydrogen. So that even if we were to leave out of view the chlorine acids, the sulfur acids, etc., no doubt can be entertained that many acids exist which contain no oxygen. Acids are compounds of electronegative bodies and a base, and in them all the electronegative electricity continues to predominate. Next to Sir Humphrey Davy, the 2 chemists who have most advanced electrochemistry are Gay-Lussac and Thénard. About the year 1808, when the attention of men of science was particularly drawn towards the galvanic battery, in consequence of the splendid discoveries of Sir Humphrey Davy, Bonaparte, who was at that time Emperor of France, consigned a sufficient sum of money to Count Cessac, governor of the Polytechnic School, to construct a powerful galvanic battery, and Gay-Lussac and Thénard were appointed to make the requisite experiments with this battery. It was impossible that a better choice could have been made. These gentlemen undertook a most elaborate and extensive set of experiments, the result of which was published in 1811, in 2 octavo volumes, under the title of Recherches physico-chimiques faites sur la pile, sur la préparation chimique et les propriétés du potassium et du sodium, sur la décomposition de l'acide boracique, sur les acides fluoriques, muriatiques et muriatique oxygène, sur l'action chimique de la lumière, sur l'analyse végétale et animale, etc. It would be difficult to name any chemical book that contains a greater number of new facts, or which contains so great a collection of important information, or which has contributed more to the advancement of chemical science. The first part contains a very minute and interesting examination of the galvanic battery, and upon what circumstances its energy depends. They tried the effect of various liquid conductors, varied the strength of the acids and of the saline solutions. This division of their labors contains much valuable information for the practical electrochemist, though it would be inconsistent with the plan of this work to enter into details. The next division of the work relates to potassium. Davy had hitherto produced that metal only in minute quantities by the action of the galvanic battery upon potash. But Gay-Lussac and Thénard contrived a process by which it can be prepared on a large scale by chemical decomposition. Their method was to put into a bent gun barrel, well coated externally with clay, and passed through a furnace, a quantity of clean iron filings. To one extremity of this barrel was fitted a tube containing a quantity of caustic potash. This tube was either shut at one end by a stopper, or by a glass tube luted to it, and plunged under the surface of mercury. To the other extremity of the gun barrel was also luted a tube, which plunged into a vessel containing mercury. Heat was applied to the gun barrel till it was heated to whiteness. Then, by means of a choffer, the caustic potash was melted and made to trickle slowly into the white-hot iron filings. At this temperature, the potash undergoes decomposition, the iron uniting with its oxygen. The potassium is disengaged, and being volatile, is deposited at a distance from the hot part of the tube, where it is collected after the process is finished. Being thus in possession both of potassium and sodium in considerable quantities, they were enabled to examine its properties more in detail than Davy had done. But such was the care and industry with which Davy's experiments had been made that very little remained to be done. The specific gravity of the two metals was determined with more precision than it was possible for Davy to do. They determined the action of these metals on water, and measured the quantity of hydrogen gas given out with more precision than Davy could. They discovered also, by heating these metals in oxygen gas, that they were capable of uniting with an additional dose of oxygen, and of forming peroxides of potassium and sodium. These oxides have a yellow color, and give out the surplus oxygen, and are brought back to the state of potash and soda when they are plunged into water. They exposed a great variety of substances to the action of potassium, and brought to light a vast number of curious and important facts, tending to throw new light on the properties and characters of that curious metallic substance. By heating together anhydrous boracic acid and potassium in a copper tube, they succeeded in decomposing the acid, and in showing it to be a compound of oxygen and a black matter like charcoal, to which the name of boron has been given. They examined the properties of boron in detail, but did not succeed in determining with exactness the proportions of the constituents of boracic acid. The subsequent experiments of Davy, though not exact, come a good deal nearer the truth. Their experiments on fluoric acid are exceedingly valuable. They first obtained that acid in a state of purity and ascertained its properties. Their attempts to decompose it, as well as those of Davy, ended in disappointment. But Ampere conceived the idea that this acid, like muriatic acid, is a compound of hydrogen with an unknown supporter of combustion, to which the name fluorine was given. This opinion was adopted by Davy, and his experiments, though they do not absolutely prove the truth of the opinion, give it at least considerable probability, and have disposed chemists in general to adopt it. The subsequent researches of Berzelius, while they have added a great deal to our former knowledge respecting fluoric acid and its compounds, have all tended to confirm and establish the doctrine that it is a hydracid, and similar in its nature to the other hydracids. But such is the tendency of fluorine to combine with every substance, that hitherto it has been impossible to obtain it in an insulated state. We want, therefore, still a decisive proof of the accuracy of the opinion. To the experiments of Gay-Lussac and Thénard on chlorine and muriatic acid, I have already alluded in a former part of this chapter. It was during their investigations connected with this subject that they discovered fluoboric acid gas, which certainly adds considerably to the probability of the theory of Ampere respecting the nature of fluoric acid. I pass over a vast number of other new and important facts and observations contained in this admirable work, which ought to be studied with minute attention by every person who aspires at becoming a chemist. Besides the numerous discoveries contained in the Recherches physico-chimiques, Gay-Lussac is the author of two of so much importance that it would be wrong to omit them. He showed that cyanogen is one of the constituents of prussic acid, succeeded in determining the composition of cyanogen, and showing it to be a compound of 2 atoms of carbon and 1 atom of azote. Prussic acid is a compound of 1 atom of hydrogen and 1 atom of cyanogen. Sulfocyanic acid, discovered by Mr. Porret, is a compound of 1 atom sulfuric and 1 atom cyanogen. Chlorocyanic acid, discovered by Berthollet, is a compound of 1 atom chlorine and 1 atom cyanogen, while cyanic acid, discovered by Wöhler, is a compound of 1 atom oxygen and 1 atom cyanogen. I take no notice of the fulminic acid, because, although Gay-Lussac's experiments are exceedingly ingenious, and his reasoning very plausible, it is not quite convincing, especially as the results obtained by Mr. Edmund Davy, and detailed by him in his late interesting memoir on this subject, are somewhat different. The other discovery of Gay-Lussac is his demonstration of the peculiar nature of iodine, his account of iodic and hydriodic acids, and of many other compounds into which that curious substance enters as a constituent. Sir H. Davy was occupied with iodine at the same time with Gay-Lussac, and his sagacity and inventive powers were too great to allow him to work upon such a substance without discovering many new and interesting facts. To M. Thénard we are indebted for the discovery of the important fact that hydrogen is capable of combining with twice as much oxygen as exists in water, and determining the properties of this curious liquid, which has been called deutoxide of hydrogen. It possesses bleaching properties in perfection, and I think it likely that chlorine owes its bleaching powers to the formation of a little deutoxide of hydrogen in consequence of its action on water. The mantle of Davy seems in some measure to have descended on Mr. Faraday, who occupies his old place at the Royal Institution. He has shown equal industry, much sagacity, and great powers of invention. The most important discovery connected with electromagnetism, next to the great fact, for which we are indebted to Professor Ørsted of Copenhagen, is due to Mr. Faraday. I mean, the rotation of the electric wires round the magnet. To him we owe the knowledge of the fact that several of the gases can be condensed into liquids by the united action of pressure and cold, which has removed the barrier that separated gaseous bodies from vapors, and shown us that all owe their elasticity to the same cause. To him also we owe the knowledge of the important fact that chlorine is capable of combining with carbon. This has considerably improved the history of chlorine, and served still further to throw new light on the analogy which exists between all the supporters of combustion. They are doubtless, all of them, capable of combining with every one of the other simple bodies, and of forming compounds with them, for they are all negative bodies, while the other simple substances without exception, when compared to them, possess positive properties. We must therefore view the history of chemistry as incomplete, till we have become acquainted with the compounds of every supporter with every simple base. End of section 63.
Section 64 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in August 2015. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 6 of the Atomic Theory, Part 1. I come now to the last improvement which chemistry has received, an improvement which has given a degree of accuracy to chemical experimenting almost approaching to mathematical precision, which has simplified prodigiously our views respecting chemical combinations, which has enabled manufacturers to introduce theoretical improvements into their processes, and to regulate with almost perfect precision the relative quantities of the various constituents necessary to produce the intended effects. The consequence of this is, that nothing is wasted, nothing is thrown away. Chemical products have become not only better in quality, but more abundant and much cheaper. I allude to the atomic theory, still only in its infancy, but already productive of the most important benefits. It is destined one day to produce still more wonderful effects, and to render chemistry not only the most delightful, but the most useful and indispensable of all the sciences. Like all other great improvements in science, the atomic theory developed itself by degrees, and several of the older chemists ascertained facts which might, had they been aware of their importance, have led them to conclusions similar to those of the moderns. The very attempt to analyze the salts was an acknowledgment that bodies united with each other in definite proportions, and these definite proportions, had they been followed out, would have led ultimately to the doctrine of atoms. For how could it be that 6 parts of potash were always saturated by 5 parts of sulphuric acid and 6.75 parts of nitric acid? How came it that 5 of sulphuric acid always went as far in saturating potash as 6.75 of nitric acid? It was known that in chemical combinations it was the ultimate particles of matter that combined. The simple explanation, therefore, would have been that the weight of an ultimate particle of sulphuric acid was only 5, while that of an ultimate particle of nitric acid was 6.75. Had such an inference been drawn, it would have led directly to the atomic theory. The atomic theory in chemistry has many points of resemblance to the fluxionary calculus in mathematics. Both give us the ratios of quantities. Both reduce investigations that would be otherwise extremely difficult, or almost impossible, to the utmost simplicity. And what is still more curious, both have been subjected to the same kind of ridicule by those who have not put themselves to the trouble of studying them with such attention as to understand them completely. The minute philosopher of Berkeley, mutatis mutandis, might be applied to the atomic theory with as much justice as to the fluxionary calculus, and I have heard more than one individual attempt to throw ridicule upon the atomic theory by nearly the same kind of arguments. The first chemists, then, who attempted to analyze the salts may be considered as contributing towards laying the foundation of the atomic theory, though they were not themselves aware of the importance of the structure, which might have been raised upon their experiments, had they been made with the requisite precision. Bergman was the first chemist who attempted regular analysis of salts. It was he that first tried to establish regular formulas for the analysis of mineral waters, stones, and ores, by the means of solution and precipitation. Hence a knowledge of the constituents of the salts was necessary, before his formulas could be applied to practice. It was to supply this requisite information that he set about analyzing the salts, and his results were long considered by chemists as exact, and employed by them to determine the results of their analysis. We now know that these analytical results of Bergman are far from accurate, that they have accordingly been laid aside as useless, but this knowledge has been derived from the progress of the atomic theory. The first accurate set of experiments to analyze the salts was made by Wenzel and published by him in 1777, in a small volume entitled Lehre von der Verwandtschaft der Körper, or Theory of the Affinities of Bodies. These analyses of Wenzel are infinitely more accurate than those of Bergman, and indeed in many cases are equally precise with the best which we have even at the present day. Yet the book fell almost dead born from the press. Wenzel's results never obtained the confidence of chemists, nor is his name ever quoted as an authority. Wenzel was struck with a phenomenon which had indeed been noticed by preceding chemists, but they had not drawn the advantages from it which it was capable of affording. There are several saline solutions which, when mixed with each other, completely decompose each other, so that two new salts are produced. Thus, if we mix together solutions of nitrate of lead and sulphate of soda in the requisite proportions, the sulphuric acid of the latter salt will combine with the oxide of lead of the former, and will form with it sulphate of lead, which will precipitate to the bottom in the state of an insoluble powder, while the nitric acid formerly united to the oxide of lead will combine with the soda formerly in union with the sulphuric acid, and form nitrate of soda, which being soluble will remain in solution in the liquid. Thus, instead of the two old salts, sulphate of soda, nitrate of lead, we obtain the two new salts, sulphate of lead, nitrate of soda. If we mix the two salts in the requisite proportions, the decomposition will be complete. But if there be an excess of one of the salts, that excess will still remain in solution without affecting the result. If we suppose the two salts anhydrous, then the proportions necessary for complete decomposition are sulphate of soda 9, nitrate of lead 20.75, total 29.75, and the quantities of the new salts formed will be sulphate of lead 19, nitrate of soda 10.75, total 29.75. We see that the absolute weights of the two sets of salts are the same. All that has happened is that both the acids and both the bases have exchanged situations. Now if, instead of mixing these two salts together in the preceding proportions, we employ sulfate of soda 9, nitrate of lead 25.75, that is to say, if we employ 5 parts of nitrate of lead more than is sufficient for the purpose, we shall have exactly the same decompositions as before, but the 5 of excess of nitrate of lead will remain in solution mixed with the nitrate of soda. There will be precipitated as before sulfate of lead 19, and there will remain in solution a mixture of nitrate of soda 10.75, nitrate of lead 5. The phenomena are precisely the same as before. The additional 5 of nitrate of lead have occasioned no alteration. The decomposition has gone on just as if they had not been present. Now, the phenomena which drew the particular attention of Wenzel is, that if the salts were neutral before being mixed, the neutrality was not affected by the decomposition which took place on their mixture. Footnote. This observation is not without exception. It does not hold when one of the salts is a phosphate or an arseniate, and this is the cause of the difficulty attending the analysis of these genera of salts. End footnote. A salt is said to be neutral when it neither possesses the characters of an acid or an alkali. Acids redden vegetable blues, while alkalis render them green. A neutral salt produces no effect whatever upon vegetable blues. This observation of Wenzel is very important. It is obvious that the salts, after their decomposition, could not have remained neutral unless the elements of the two salts had been such that the bases in each just saturated the acids in either of the salts. The constituents of the two salts are as follows. 9 sulfate of soda are 5 sulfuric acid, 4 soda. 20.75 nitrate of lead are 6.75 nitric acid, 14 oxide of lead. Now it is clear that, unless 5 sulfuric acid were just saturated by 4 soda and by 14 oxide of lead, and 6.75 of nitric acid by the same 4 soda and 14 oxide of lead, the salts, after their decomposition, could not have preserved their neutrality. Had 4 soda required only 5.75 of nitric acid, or had 14 oxide of lead required only 4 sulfuric acid to saturate them, the liquid after decomposition would have contained an excess of acid. As no such excess exists, it is clear that in saturating an acid, 4 soda goes exactly as far as 14 oxide of lead, and that in saturating a base, 5 sulfuric acid goes just as far as 6.75 nitric acid. Nothing can exhibit in a more striking point of view the almost despotic power of fashion and authority over the minds even of men of science, and the small number of them that venture to think for themselves, than the fact that this most important and luminous explanation of Wenzel, confirmed by much more accurate experience than any which chemistry has yet seen, is scarcely noticed by any of his contemporaries, and seems not to have attracted the smallest attention. In science it is as unfortunate for a man to get before the age in which he lives as to continue behind it. The admirable explanation of combustion by Hooke, and the important experiments on combustion and respiration by Mayow, were lost upon their contemporaries, and procured them little or no reputation whatever, while the same theory and the same experiments, advanced by Lavoisier and Priestley a century later, when the minds of men of science were prepared to receive them, raised them to the very first rank among philosophers, and produced a revolution in chemistry. So much concern has fortune, not merely in the success of kings and conquerors, but in the reputation acquired by men of science. In the year 1792 another laborer, in the same department of chemistry, appeared. This was Jeremiah Benjamin Richter, a Prussian chemist, of whose history I know nothing more than that his publications were printed and published in Breslau, from which I infer that he was a native of, or at least resided in, Silesia. He calls himself Assessor of the Royal Prussian Mines and Smelting Houses, and Arcanist of the Commission of Berlin Porcelain Manufacture. He died in the prime of life on the 4th of May 1807. In the year 1792 he published a work entitled Anfangsgründe der Stochiometrie oder Messkunst chemischer Elemente, Elements of Stoichiometry, or the Mathematics of the Chemical Elements. A second and third volume of this work appeared in 1793, and a fourth volume in 1794. The object of this book was a rigid analysis of the different salts, founded on the fact just mentioned, that when two salts decompose each other, the salts newly formed are neutral as well as those which have been decomposed. He took up the subject nearly in the same way as Wenzel had done, but carried the subject much further, and endeavored to determine the capacity of saturation of each acid and base, and to attach numbers to each, indicating the weights which mutually saturate each other. He gave the whole subject a mathematical dress, and endeavored to show that the same relation existed between the numbers representing the capacity of saturation of these bodies as does between certain classes of figure-8 numbers. When we strip the subject of the mystical form under which he presented it, the labors of Richter may be exhibited under the two following tables, which represent the capacity of saturation of the acids and bases according to his experiments. Table 1. Acids. Fluoric acid, 427. Carbonic acid, 577. Sebacic acid, 706. Muriatic acid, 712. Oxalic acid, 755. Phosphoric acid, 979. Formic acid, 988. Sulfuric acid, 1000. Succinic acid, 1209. Nitric acid, 1405. Acetic acid, 1480. Citric acid, 1683. Tartaric acid, 1694. Table 2. Bases. Alumina, 525. Magnesia, 615. Ammonia, 672. Lime, 793. Soda, 859. Strontium, 1329. Potash, 1605. Barytes, 2222. To understand this table, it is only necessary to observe that if we take the quantity of any of the acids placed after it in the table, that quantity will be exactly saturated by the weight of each base put after it in the second column. Thus, 1000 of sulfuric acid will be just saturated by 525 alumina, 615 magnesia, 672 ammonia, 733 lime, and so on. On the other hand, the quantity of any base placed after its name in the second column will be just saturated by the weight of each acid placed after its name in the first column. Thus, 793 parts of lime will be just saturated by 427 of fluoric acid, 577 of carbonic acid, 706 of sebacic acid, and so on. This work of Richter was followed by a periodical work entitled Über die neuen Gegenstände der Chemie, on the new objects of chemistry. This work was begun in the year 1792 and continued in 12 different numbers, or volumes, to the time of his death in 1807. Footnote. I have only seen 11 parts of this work, the last of which appeared in 1802, but I believe that the 12th part was published afterwards. End footnote. Richter's labours in this important field produced as little attention as those of Wenzel. Gehlen wrote a short panegyric upon him at his death, praising his views and pointing out their importance, but I am not aware of any individual, either in Germany or elsewhere, who adopted Richter's opinions during his lifetime, or even seemed aware of their importance, unless we are to accept Berthollet, who mentions them with approbation in his Chemical Statics. This inattention was partly owing to the great want of accuracy which it is impossible not be sensible of in Richter's experiments. He operated upon too large quantities of matter, which indeed was the common defect of the times, and was first checked by Dr. Wollaston. The dispute between the phlogistians and the antiphlogistians, which was not fully settled in Richter's time, drew the attention of chemists to another branch of the subject. Richter in some measure went before the age in which he lived, and had his labours not been recalled to our recollection by the introduction of atomic theory, he would probably have been forgotten, like Hooke and Mayow, and only brought again under review after the new discoveries in the science had put it in the power of chemists in general to appreciate the value of his labours. It is to Mr. Dalton that we are indebted for the happy and simple idea from which the atomic theory originated. End of section 64. Section 65 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in September 2015. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 6 of the Atomic Theory, Part 2. John Dalton, to whose lot it has fallen to produce such an alteration and improvement in chemistry, was born in Westmoreland, and belongs to that small and virtuous sect known in this country by the name of Quakers. When very young he lived with Mr. Gow of Kendal, a blind philosopher, to whom he read and whom he assisted in his philosophical investigation. It was here, probably, that he acquired a considerable part of his education, particularly his taste for mathematics. For Mr. Gow was remarkably fond of mathematical investigations, and has published several mathematical papers that do him credit. From Kendal Mr. Dalton went to Manchester about the beginning of the present century, and commenced teaching elementary mathematics to such young men as felt inclined to acquire some knowledge of that important subject. In this way, together with a few courses of lectures on chemistry, which he has occasionally given at the Royal Institution in London, at the Institution in Birmingham, in Manchester, and once in Edinburgh and in Glasgow, he has contrived to support himself for more than 30 years, if not in affluence, at least in perfect independence. And as his desires have always been of the most moderate kind, his income has always been equal to his wants. In a country like this, where so much wealth abounds, and where so handsome a yearly income was subscribed to enable Dr. Priestley to prosecute his investigations undisturbed and undistracted by the necessity of providing for the daily wants of his family, there is little doubt that Mr. Dalton, had he so chosen it, might, in point of pecuniary circumstances, have exhibited a much more brilliant figure. But he has displayed a much nobler mind by the career which he has chosen, equally regardless of riches as the most celebrated sages of antiquity, and as much respected and beloved by his friends, even in the rich commercial town of Manchester, as if he were one of the greatest and most influential men in the country. Towards the end of the last century, a literary and scientific society had been established in Manchester, of which Mr. Thomas Henry, the translator of Lavoisier's essays, and who distinguished himself so much in promoting the introduction of the new mode of bleaching into Lancashire, was long President. Mr. Dalton, who had already distinguished himself by his meteorological observations, and particularly by his account of the aurora borealis, soon became a member of the Society, and in the 5th volume of their Memoirs, Part II, published in 1802, 6 papers of his were inserted, which lay the foundation of his future celebrity. These papers were chiefly connected with meteorological subjects, but by far the most important of them all was the one entitled Experimental Essays on the Constitution of Mixed Gases, on the force of steam or vapour from water and other liquids in different temperatures, both in a Torricellian vacuum and in air, on evaporation, and on the expansion of gases by heat. From a careful examination of all the circumstances, he considered himself as entitled to infer that when two elastic fluids or gases, A and B, are mixed together, there is no mutual repulsion among their particles. That is, the particles of A do not repel those of B as they do one another. Consequently, the pressure or whole weight upon any one particle arises solely from those of its own kind. This doctrine is of so startling a nature and so contrary to the opinions previously received, that chemists have not been much disposed to admit it. But at the same time it must be confessed that no one has hitherto been able completely to refute it. The consequences of admitting it are obvious. We should be able to account for a fact which has been long known, though no very satisfactory reason for it had been assigned, namely, that if two gases be placed in two separate vessels, communicating by a narrow orifice, and left at perfect rest in a place where the temperature never varies, if we examine them after a certain interval of time, we shall find both equally diffused through both vessels. If we fill a glass phial with hydrogen gas and another phial with common air or carbonic acid gas, and unite the two phials by a narrow glass tube 2 feet long, filled with common air, and place the phial containing the hydrogen gas uppermost, and the other perpendicularly below it, the hydrogen, though lightest, will not remain in the upper phial, nor the carbonic acid, though heaviest, in the undermost phial, but we shall find both gases equally diffused through both phials. But the second of these essays is by far the most important. In it he establishes, by the most unexceptionable evidence, that water, when it evaporates, is always converted into an elastic fluid, similar in its properties to air. But that the distance between the particles is greater, the lower the temperature is at which the water evaporates. The elasticity of this vapor increases as the temperature increases. At 32 degrees it is capable of balancing a column of mercury about half an inch in height, and at 212 degrees it balances a column 30 inches high, or it is then equal to the pressure of the atmosphere. He determined the elasticity of vapor at all temperatures from 32 degrees to 212 degrees, pointed out the method of determining the quantity of vapor that at any time exists in the atmosphere, the effect which it has upon the volume of air, and the mode of determining its quantity. Finally, he determined, experimentally, the rate of evaporation from the surface of water at all temperatures from 32 degrees to 212 degrees. These investigations have been of infinite use to chemists in all their investigations respecting the specific gravity of gases, and have enabled them to resolve various interesting problems, both respecting specific gravity, evaporation, rain and respiration, which, had it not been for the principles laid down in this essay, would have eluded their grasp. In the last essay contained in this paper he has shown that all elastic fluids expend the same quantity by the same addition of heat, and this expansion is very nearly 1/480th part for every degree of Fahrenheit's thermometer. In this last branch of the subject Mr. Dalton was followed by Gay-Lussac, who, about half a year after the appearance of his essays, published a paper in the Annales de Chimie, showing that the expansion of all elastic fluids, when equally heated, is the same. Mr. Dalton concluded that the expansion of all elastic fluids by heat is equable. And this opinion has been since confirmed by the important experiments of Dulong and Petit, which have thrown much additional light on the subject. In the year 1804, on the 26th of August, I spent a day or two at Manchester, and was much with Mr. Dalton. At that time he explained to me his notions respecting the composition of bodies. I wrote down at the time the opinions which he offered, and the following account is taken literally from my journal of that date. The ultimate particles of all simple bodies are atoms incapable of further division. These atoms, at least viewed along with their atmospheres of heat, are all spheres, and are each of them possessed of particular weights, which may be denoted by numbers. For the greater clearness he represented the atoms of the simple bodies by symbols. The following are his symbols for 4 simple bodies, together with the numbers attached to them by him in 1804. Circle, oxygen, relative weight 6.5. Dotted circle, hydrogen, relative weight 1. Black disk, carbon, relative weight 5. Circle with line, azote, relative weight 5. The following symbols represent the way in which he thought these atoms were combined to form certain binary compounds, with the weight of an integrant particle of each compound. Circle, dotted circle, water, weight 7.5. Circle, circle with line, nitrous gas, weight 11.5. Black disk, dotted circle, olefiant gas, weight 6. Circle with line, dotted circle, ammonia, weight 6. Circle, black disk, carbonic oxide, weight 11.5. The following were the symbols by which he represented the composition of certain tertiary compounds. Circle, black disk, circle, carbonic acid, weight 18. Circle, circle with line, circle, nitrous oxide, weight 16.5. Black disk, dotted circle, black disk, ether, weight 11. Dotted circle, black disk, dotted circle, carburetted hydrogen, weight 7. Circle, circle with line, circle, nitric acid, weight 18. A quaternary compound, in 2 rows. First row, circle, circle with line, circle. Second row, empty, circle, empty. Oxynitric acid, weight 24.5. A quinquennary compound, in 4 columns. First column, circle with line. Second column, on top of each other, circle, circle. Third column, circle with line. Fourth column, circle. Nitrous acid, weight 29.5. A sexternary compound, in a 2x3 matrix. First row, black disk, circle, black disk. Second row, dotted circle, black disk, dotted circle. Alcohol, weight 23.5. These symbols are sufficient to give the reader an idea of the notions entertained by Dalton respecting the nature of compounds. Water is a compound of one atom oxygen and one atom hydrogen, as it is obvious from the symbol circle, dotted circle. Its weight 7.5 is that of an atom of oxygen and an atom of hydrogen united together. In the same way, carbonic oxide is a compound of one atom oxygen and one atom carbon. Its symbol is circle, black disk, and its weight 11.5 is equal to an atom of oxygen and an atom of carbon added together. Carbonic acid is a tertiary compound, or it consists of 3 atoms united together, namely 2 atoms of oxygen and 1 atom of carbon. Its symbol is circle, black disk, circle, and its weight 18. A bare inspection of the symbols and weights will make Mr. Dalton's notions respecting the constitution of every body in the table evident to every reader. It was this happy idea of representing the atoms and constitution of bodies by symbols that gave Mr. Dalton's opinions so much clearness. I was delighted with the new light which immediately struck my mind, and saw at a glance the immense importance of such a theory when fully developed. Mr. Dalton informed me that the atomic theory first occurred to him during his investigations of olefiant gas and carburetted hydrogen gases, at that time imperfectly understood, and the constitution of which was first fully developed by Mr. Dalton himself. It was obvious from the experiments which he made upon them that the constituents of both were carbon and hydrogen, and nothing else. He found further that if we reckon the carbon in each the same, then carburetted hydrogen gas contains exactly twice as much hydrogen as olefiant gas does. This determined him to state the ratios of these constituents in numbers, and to consider the olefiant gas as a compound of 1 atom of carbon and 1 atom of hydrogen, and carburetted hydrogen of 1 atom of carbon and 2 atoms of hydrogen. The idea thus conceived was applied to carbonic oxide, water, ammonia, etc., and numbers representing the atomic weights of oxygen, azote, etc., deduced from the best analytical experiments which chemistry then possessed. Let not the reader suppose that this was an easy task. Chemistry at that time did not possess a single analysis which could be considered as even approaching to accuracy. A vast number of facts had been ascertained, and a fine foundation laid for future investigation, but nothing, as far as weight and measure were concerned, deserving the least confidence, existed. We need not be surprised, then, that Mr. Dalton's first numbers were not exact. It required infinite sagacity and not a little labor to come so near the truth as he did. How could accurate analyses of gases be made when there was not a single gas whose specific gravity was known with even an approach to accuracy? The preceding investigations of Dalton himself paved the way for accuracy in this indispensable department, but still accurate results had not yet been obtained. In the 3rd edition of my System of Chemistry, published in 1807, I introduced a short sketch of Mr. Dalton's theory, and thus made it known to the chemical world. The same year a paper of mine on oxalic acid was published in the Philosophical Transactions, in which I showed that oxalic acid unites in 2 proportions with strontian, forming an oxalate and binoxalate, and that, supposing the strontian in both salts to be the same, the oxalic acid in the latter is exactly twice as much as in the former. About the same time, Dr. Wollaston showed that bicarbonate of potash contains just twice the quantity of carbonic acid that exists in carbonate of potash, and that there are 3 oxalates of potash, that is, oxalate, binoxalate, and quadroxalate, the weight of acids in each of which are as the numbers 1, 2, 4. These facts gradually drew the attention of chemists to Mr. Dalton's views. There were, however, some of our most eminent chemists who were very hostile to the atomic theory. The most conspicuous of these was Sir Humphry Davy. In the autumn of 1807 I had a long conversation with him at the Royal Institution, but could not convince him that there was any truth in the hypothesis. A few days after I dined with him at the Royal Society Club, at the Crown and Anchor, in the Strand. Dr. Wollaston was present at the dinner. After dinner every member of the club left the tavern, except Dr. Wollaston, Mr. Davy, and myself, who stayed behind and had tea. We sat about an hour and a half together, and our whole conversation was about the atomic theory. Dr. Wollaston was a convert as well as myself, and we tried to convince Davy of the inaccuracy of his opinions. But, so far from being convinced, he went away, if possible, more prejudiced against it than ever. Soon after, Davy met Mr. Davis Gilbert, the late distinguished President of the Royal Society, and he amused him with a caricature description of the atomic theory, which he exhibited in so ridiculous a light that Mr. Gilbert was astonished how any man of sense or science could be taken in with such a tissue of absurdities. Mr. Gilbert called on Dr. Wollaston, probably to discover what could have induced a man of Dr. Wollaston's sagacity and caution to adopt such opinions, and was not sparing in laying the absurdities of the theory, such as they had been represented to him by Davy, in the broadest point of view. Dr. Wollaston begged Mr. Gilbert to sit down and listen to a few facts which he would state to him. He then went over all the principal facts at that time known respecting the salts, mentioned the alkaline carbonates and bicarbonates, the oxalate, binoxalate, and quadroxalate of potash, carbonic oxide and carbonic acid, olefiant gas and carburetted hydrogen, and doubtless many other similar compounds, in which the proportion of one of the constituents increases in a regular ratio. Mr. Gilbert went away a convert to the truth of the atomic theory, and he had the merit of convincing Davy that his former opinions of the subject were wrong. What arguments he employed I do not know, but they must have been convincing ones, for Davy ever after became a strenuous supporter of the atomic theory. The only alteration which he made was to substitute proportion for Dalton's word atom. Dr. Wollaston substituted for it the term equivalent. The object of these substitutions was to avoid all theoretical enunciations. But, in fact, these terms, proportion, equivalent, are neither of them so convenient as the term atom, and unless we adopt the hypothesis with which Dalton set out, namely that the ultimate particles of bodies are atoms incapable of further division, and that chemical combination consists in the union of these atoms with each other, we lose all the new light which the atomic theory throws upon chemistry, and bring our notions back to the obscurity of the days of Bergman and of Berthollet. In the year 1808 Mr. Dalton published the first volume of his New System of Chemical Philosophy. This volume consists chiefly of 2 chapters. The first, on heat, occupies 140 pages. In it he treats of all the effects of heat, and shows the same sagacity and originality which characterize all his writings. Even when his opinions on a subject are not correct, his reasoning is so ingenious and original, and the new facts which he contrives to bring forward so important, that we are always pleased and always instructed. The second chapter, on the Constitution of Bodies, occupies 70 pages. The chief object of it is to combat the peculiar notions respecting elastic fluids which had been advanced by Berthollet and supported by Dr. Murray of Edinburgh. In the third chapter, on chemical synthesis, which occupies only a few pages, he gives us the outlines of the atomic theory, such as he had conceived it. In a plate at the end of the volume he exhibits the symbols and atomic weights of 37 bodies, 20 of which were then considered as simple, and the other 17 as compound. The following table shows the atomic weight of the simple bodies, as he at that time had determined them from the best analytical experience that had been made. Hydrogen. Weight of atom 1. Azote. Weight of atom 5. Carbon. Weight of atom 5. Oxygen. Weight of atom 7. Phosphorus. Weight of atom 9. Sulfur. Weight of atom 13. Magnesia. Weight of atom 20. Lime. Weight of atom 23. Soda. Weight of atom 28. Potash. Weight of atom 42. Strontium. Weight of atom 46. Barytes. Weight of atom 68. Iron. Weight of atom 38. Zinc. Weight of atom 56. Copper. Weight of atom 56. Lead. Weight of atom 95. Silver. Weight of atom 100. Platinum. Weight of atom 100. Gold. Weight of atom 140. Mercury. Weight of atom 167. He had made choice of hydrogen for unity because it is the lightest of all bodies. He was of opinion that the atomic weights of all other bodies are multiples of hydrogen, and accordingly they are all expressed in whole numbers. He had raised the atomic weight of oxygen from 6.5 to 7, from a more careful examination of the experiments on the component parts of water. Davy, from a more accurate set of experiments, soon after raised the number for oxygen to 7.5, and Dr. Prout, from a still more careful investigation of the relative specific gravities of oxygen and hydrogen, showed that if the atom of hydrogen be 1, that of oxygen must be 8. Everything conspires to prove that this is the true ratio between the atomic weights of oxygen and hydrogen. In 1810 appeared the second volume of Mr. Dalton's New System of Chemical Philosophy. In it he examines the elementary principles or simple bodies, namely oxygen, hydrogen, azote, carbon, sulfur, phosphorus, and the metals, and the compounds consisting of two elements, namely the compounds of oxygen with hydrogen, azote, carbon, sulfur, phosphorus, of hydrogen with azote, carbon, sulfur, phosphorus. Finally he treats of the fixed alkalis and earths. All these combinations are treated of with infinite sagacity, and he endeavors to determine the atomic weights of the different elementary substances. Nothing can exceed the ingenuity of his reasoning. But unfortunately at that time very few accurate chemical analyses existed, and in chemistry no reasoning, however ingenious, can compensate for this indispensable datum. Accordingly his table of atomic weights at the end this second volume, though much more complete than that at the end of the first volume, is still exceedingly defective. Indeed, no one number can be considered as perfectly correct. The third volume of the New System of Chemical Philosophy was only published in 1827, but the greatest part of it had been printed nearly 10 years before. It treats of the metallic oxides, the sulphurets, phosphorates, carburettes, and alloys. Doubtless many of the facts contained in it were new when the sheets were put to the press, but during the interval between the printing and publication almost the whole of them had not merely been anticipated, but the subject carried much further. By far the most important part of the volume is the appendix, consisting of about 90 pages, in which he discusses, with his usual sagacity, various important points connected with heat and vapor. In page 352 he gives a new table of the atomic weights of bodies, much more copious than those contained in the two preceding volumes, and into which he has introduced the corrections necessary from the numerous correct analyses which had been made in the interval. He still adheres to the ratio 1:7 as the correct difference between the weights of the atoms of hydrogen and oxygen. This shows very clearly that he has not attended to the new facts which have been brought forward on the subject. No person who has attended to the experiments made on the specific gravity of these two gases during the last 12 years could admit that these specific gravities are to each other as 1:14. If 1:16 be not the exact ratio, it will surely be admitted on all hands that it is infinitely near it. Mr. Dalton represented the weight of an atom of hydrogen by 1 because it is the lightest of bodies. In this he has been followed by the chemists of the Royal Institution, by Mr. Phillips, Dr. Henry, and Dr. Turner, and perhaps some others whose names I do not at present recollect. Dr. Wollaston, in his paper on chemical equivalents, represented the atomic weight of oxygen by 1, because it enters into a greater number of combinations than any other substance, and this plan has been adopted by Berzelius, by myself, and by the greater number, if not the whole, of the chemists on the continent. Perhaps the advantage which Dr. Wollaston assigned for making the atom of oxygen unity will ultimately disappear, for there is no reason for believing that the other supporters of combustion are not capable of entering into as many compounds as oxygen. But, from the constitution of the atmosphere, it is obvious that the compounds into which oxygen enters will always be of more importance to us than any others, and in this point of view it may be attended with considerable convenience to have oxygen represented by 1. In the present state of the atomic theory there is another reason for making the atom of oxygen unity, which I think of considerable importance. Chemists are not yet agreed about the atom of hydrogen. Some consider water a compound of 1 atom of oxygen and 2 atoms of hydrogen, others of 1 atom of oxygen and 1 atom of hydrogen. According to the first view, the atom of hydrogen is only 1/16 of the weight of an atom of oxygen; according to the second, it is 1/8. If, therefore, we were to represent the atom of hydrogen by 1, the consequence would be that 2 tables of atomic weights would be requisite, all the atoms in one being double the weight of the atoms in the other, whereas, if we make the atom of oxygen unity, it will be the atom of hydrogen only that will differ in the 2 tables. In the one table it will be 0.125, in the other it will be 0.0625, or, reckoning with Berzelius, the atom of oxygen equals 100, we have that of hydrogen equals 12.5 or 6.25, according as we view water to be a compound of 1 atom of oxygen with 1 or 2 atoms of hydrogen. End of section 65. Section 66 of The History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in August 2015. The History of Chemistry by Thomas Thomson, Volume 2, Chapter 6, of the Atomic Theory, Part 3. In the year 1809, Gay-Lussac published in the second volume of the Mémoires d'Arcueil a paper on the union of the gaseous substances with each other. In this paper he shows that the proportions in which the gases unite with each other are of the simplest kind. 1 volume of one gas either combining with 1 volume of another, or with 2 volumes, or with half a volume. The atomic theory of Dalton had been opposed with considerable keenness by Berthollet in his introduction to the French translation of my System of Chemistry. Nor was this opposition to be wondered at, because its admission would of course overturn all the opinions which Berthollet had labored to establish in his Chemical Statics. The object of Gay-Lussac's paper was to confirm and establish the new atomic theory by exhibiting it in a new point of view. Nothing can be more ingenious than his mode of treating the subject, or more complete than the proofs which he brings forward in support of it. It had been already established that water is formed by the union of 1 volume of oxygen and 2 volumes of hydrogen gas. Gay-Lussac found by experiment that 1 volume of muriatic acid gas is just saturated by 1 volume of ammoniacal gas. The product is sal ammoniac. Fluoroboric acid gas unites in 2 proportions with ammoniacal gas. The first compound consists of 1 volume of fluoroboric gas and 1 volume of ammoniacal, the second of 1 volume of the acid gas and 2 volumes of the alkaline. The first forms a neutral salt, the second an alkaline salt. He showed likewise that carbonic acid and ammoniacal gas could combine also in 2 proportions, namely 1 volume of the acid gas with 1 or 2 volumes of the alkaline gas. M. Amédée Berthollet had proved that ammonia is a compound of 1 volume of azotic and 3 volumes of hydrogen gas. Gay-Lussac himself had shown that sulphuric acid is composed of 1 volume sulphurous acid gas and a half volume of oxygen gas. He showed further that the compounds of azote and oxygen were composed as follows: protoxide of azote, 1 volume azote plus 1/2 volume oxygen. Deutoxide of azote, 1 volume of azote plus 1 volume of oxygen. Nitrous acid, 1 volume of azote plus 2 volumes of oxygen. He showed also that when the 2 gases after combining remained in the gaseous state, the diminution of volume was either 0, or 1/3, or 1/2. The constancy of these proportions left no doubt that the combinations of all gaseous bodies were definite. The theory of Dalton applied to them with great facility. We have only to consider a volume of gas to represent an atom, and then we see that in gases 1 atom of 1 gas combines either with 1, 2, or 3 atoms of another gas, and never with more. There is, indeed, a difficulty occasioned by the way in which we view the composition of water. If water be composed of 1 atom of oxygen and 1 atom of hydrogen, then it follows that a volume of oxygen contains twice as many atoms as a volume of hydrogen. Consequently, if a volume of hydrogen gas represent an atom, half a volume of oxygen gas must represent an atom. Dr. Prout soon after showed that there is an intimate connection between the atomic weight of a gas and its specific gravity. This indeed is obvious at once. I afterwards showed that the specific gravity of a gas is either equal to its atomic weight multiplied by 1.1111, etc., the specific gravity of oxygen gas, or by 0.55555, etc., half the specific gravity of oxygen gas, or by 0.27777, etc., 1/4 of the specific gravity of oxygen gas, these differences depending upon the relative condensation which the gases undergo when their elements unite. The following table exhibits the atoms and specific gravity of these 3 sets of gases. 1. Specific gravity equals atomic weight times 1.1111. Oxygen gas, atomic weight 1, specific gravity 1.1111. Fluorosilicic acid, atomic weight 3.25, specific gravity 3.6111. 2. Specific gravity equals atomic weight times 0.5555, etc. Hydrogen, atomic weight 0.125, specific gravity 0.0694. Azotic, atomic weight 1.75, specific gravity 0.0722. Chlorine, atomic weight 4.5, specific gravity 2.5. Carbon vapor, atomic weight 0.75, specific gravity 0.4166. Phosphorus vapor, atomic weight 2, specific gravity 1.1111. Sulfur vapor, atomic weight 2, specific gravity 1.1111. Tellurium vapor, atomic weight 4, specific gravity 2.2222. Arsenic vapor, atomic weight 4.75, specific gravity 2.6388. Selenium vapor, atomic weight 5, specific gravity 2.7777. Bromine vapor, atomic weight 10, specific gravity 5.5555. Iodine vapor, atomic weight 15.75, specific gravity 8.75. Steam, atomic weight 1.125, specific gravity 0.625. Carbonic oxide gas, atomic weight 1.75, specific gravity 0.9722. Carbonic acid, atomic weight 2.75, specific gravity 1.5277. Protoxide of azote, atomic weight 2.75, specific gravity 1.5277. Nitric acid vapor, atomic weight 6.75, specific gravity 3.75. Sulfurous acid, atomic weight 4, specific gravity 2.2222. Sulfuric acid vapor, atomic weight 5, specific gravity 2.7777. Cyanogen, atomic weight 3.25, specific gravity 1.8055. Fluoboric acid, atomic weight 4.25, specific gravity 2.3611. Bisulfurate of carbon, atomic weight 4.75, specific gravity 2.6388. Chlorocarbonic acid, atomic weight 6.25, specific gravity 3.4722. 3. Specific gravity equals atomic weight times 0.27777, etc. Ammoniacal gas, atomic weight 2.125, specific gravity 0.59027. Hydrocyanic acid, atomic weight 3.375, specific gravity 0.9375. Deutoxide of azote, atomic weight 3.75, specific gravity 1.0416. Muriatic acid, atomic weight 4.625, specific gravity 1.28472. Hydrobromic acid, atomic weight 10.125, specific gravity 2.8125. Hydriodic acid, atomic weight 15.875, specific gravity 4.40973. When Professor Berzelius of Stockholm thought of writing his elementary treatise on chemistry, the first volume of which was published in the year 1808, he prepared himself for the task by reading several chemical works which do not commonly fall under the eyes of those who compose elementary treatises. Among other books he read the Stoichiometry of Richter, and was much struck with the explanations there given of the composition of salts, and the precipitation of metals by each other. It followed from the researches of Richter that if we were in possession of good analysis of certain salts, we might by means of them calculate with accuracy the composition of all the rest. Berzelius formed immediately the project of analyzing a series of salts with the most minute attention to accuracy. While employed in putting this project in execution, Davy discovered the constituents of the alkalis and earths, Mr. Dalton gave to the world his notions respecting the atomic theory, and Gay-Lussac made known his theory of volumes. This greatly enlarged his views as he proceeded, and induced him to embrace a much wider field than he had originally contemplated. His first analyses were unsatisfactory, but by repeating them and varying the methods, he detected errors, improved his processes, and finally obtained results which agreed exceedingly well with the theoretical calculations. These laborious investigations occupied him several years. The first outline of his experiments appeared in the 77th volume of the Annales de Chimie in 1811, in a letter addressed by Berzelius to Berthollet. In this letter he gives an account of his methods of analysis together with the composition of 47 compound bodies. He shows that when a metallic protosulfuret is converted into a sulfate, the sulfate is neutral; that an atom of sulfur is twice as heavy as an atom of oxygen, and that when sulfite of barytes is converted into sulfate, the sulfite is neutral, there being no excess either of acid or base. From these and many other important facts he finally draws this conclusion: quote, "In a compound formed by the union of two oxides, the one which, when decomposed by the galvanic battery, attaches itself to the positive pole, the acid for example, contains 2, 3, 4, 5, etc. times as much oxygen as the one which attaches itself to the negative pole, the alkali, earth, or metallic oxide." End quote. Berzelius's essay itself appeared in the third volume of the Afhandlingar in 1810. It was almost immediately translated into German and published by Gilbert in his Annalen der Physik. But no English translation has ever appeared, the editors of our periodical works being in general unacquainted with the German and other northern languages. In 1815 Berzelius applied the atomic theory to the mineral kingdom, and showed with infinite ingenuity that minerals are chemical compounds in definite or atomic proportions, and by far the greater number of them combinations of acids and bases. He applied the theory also to the vegetable kingdom by analyzing several of the vegetable acids and showing their atomic constitution. But here a difficulty occurs, which in the present state of our knowledge we are unable to surmount. There are two acids, the acetic and succinic, that are composed of exactly the same number and same kind of atoms, and whose atomic weight is 6.25. The constituents of these two acids are 2 atoms hydrogen, atomic weight 0.25, 4 atoms carbon, atomic weight 3, 3 atoms oxygen, atomic weight 3. Total atomic weight 6.25. So that they consist of 9 atoms. Now, as these two acids are composed of the same number and the same kind of atoms, one would expect that their properties should be the same, but this is not the case. Acetic acid has a strong and aromatic smell. Succinic acid has no smell whatever. Acetic acid is so soluble in water that it is difficult to obtain it in crystals, and it cannot be procured in a separate state free from water, for the crystals of acetic acid are composed of 1 atom of acid and 1 atom of water united together. But succinic acid is not only easily obtained free from water, but it is not even very soluble in that liquid. The nature of the salts formed by these two acids is quite different. The action of heat upon each is quite different. The specific gravity of each differs. In short, all their properties exhibit a striking contrast. Now, how are we to account for this? Undoubtedly by the different ways in which the atoms are arranged in each. If the electrochemical theory of combination be correct, we can only view atoms as combining 2 by 2. A substance, then, containing 9 atoms, such as acetic acid, must be of a very complex nature. And it is obvious enough that these 9 atoms might arrange themselves in a great variety of binary compounds, and the way in which these binary compounds unite may, and doubtless does, produce a considerable effect upon the nature of the compound formed. Thus, if we make use of Mr. Dalton's symbols to represent the atoms of hydrogen, carbon, and oxygen, we may suppose the 9 atoms constituting acetic and succinic acid to be arranged thus in a 3 by 3 matrix. First row, dotted circle, black disk, dotted circle. Second row, circle, circle, circle. Third row, black disk, black disk, black disk. Or thus in a 3 by 3 matrix. First row, black disk, dotted circle, black disk. Second row, circle, circle, circle. Third row, black disk, dotted circle, black disk. Now, undoubtedly these two arrangements would produce a great change in the nature of the compound. There is something in the vegetable acids quite different from the acids of the inorganic kingdom, and which would lead to the suspicion that the electrochemical theory will not apply to them as it does to the others. In the acids of carbon, sulfur, phosphorus, selenium, etc., we find 1 atom of a positive substance united to 1, 2, or 3 of a negative substance. We are not surprised, therefore, to find the acid formed negative also. But in acetic and succinic acids we find every atom of oxygen united with 2 electropositive atoms. The wonder then is that the acid should not only retain its electronegative properties, but that it should possess considerable power as an acid. In benzoic acid, for every atom of oxygen, there are present no fewer than 7 electropositive atoms. Berzelius has returned to these analytical experiments repeatedly, so that at last he has brought his results very near the truth indeed. It is to his labors chiefly that the great progress which the atomic theory has made is owing. In the year 1814 there appeared in the Philosophical Transactions a description of a synoptical scale of chemical equivalents by Dr. Wollaston. In this paper we have the equivalents or atomic weights of 73 different bodies, deduced chiefly from a sagacious comparison of the previous analytical experiments of others, and almost all of them very near the truth. These numbers are laid down upon a sliding rule by means of a table of logarithms, and over against them the names of the substances. By means of this rule a great many important questions respecting the substances contained on the scale may be solved. Hence the scale is of great advantage to the practical chemist. It gives, by bare inspection, the constituents of all the salts contained on it, the quantity of any other ingredient necessary to decompose any salt, and the weights of the new constituents that will be formed. The contrivance of this scale, therefore, may be considered as an important addition to the atomic theory. It rendered that theory everywhere familiar to all those who employed it. To it chiefly we owe, I believe, the currency of that theory in Great Britain, and the prevalence of the mode which Dr. Wollaston introduced, namely, of representing the atom of oxygen by unity, or at least by 10, which comes nearly to the same thing. Perhaps the reader will excuse me if to the preceding historical details I add a few words to make him acquainted with my own attempts to render the atomic theory more accurate by new and careful analysis. I shall not say anything respecting the experiments which I undertook to determine the specific gravity of the gases, though they were performed with much care and at a considerable expense, and though I believe the results obtained approached accuracy as nearly as the present state of chemical apparatus enables us to go. In the year 1819 I began a set of experiments to determine the exact composition of the salts containing the different elementary bodies by means of double decomposition, as was done by Wenzel, conceiving that in that way the results would be very near the truth, while the experiments would be more easily made. My mode was to dissolve, for example, a certain weight of muriate of barytes in distilled water, and then to ascertain by repeated trials what weight of sulphate of soda must be added to precipitate the whole of the barytes without leaving any surplus of sulphuric acid in the liquid. To determine this I put into a watch-glass a few drops of the filtered liquor consisting of the mixture of solutions of the two salts. To this I added a drop of solution of sulphate of soda. If the liquid remained clear, it was a proof that it contained no sensible quantity of barytes. To another portion of the liquid, also in a watch-glass, I added a drop of muriate of barytes. If there was no precipitate, it was a proof that the liquid contained no sensible quantity of sulphuric acid. If there was a precipitate, on the addition of either of these solutions, it showed that there was an excess of one or other of the salts. I then mixed the two salts in another proportion, and proceeded in this way till I had found two quantities which when mixed exhibited no evidence of the residual liquid containing any sulphuric acid or barytes. I considered these two weights of the salts as the equivalent weights of the salt, or as weights proportional to an integrant particle of each salt. I made no attempt to collect the two new formed salts and to weigh them separately. I published the result of my numerous experiments in 1825 in a work entitled An Attempt to Establish the First Principles of Chemistry by Experiment. The most valuable part of this book is the account of the salts, about 300 of which I subjected to actual analysis. Of these the worst executed are the phosphates, for with respect to them I was sometimes misled by my method of double decomposition. I was not aware at first that in certain cases the proportion of acid in these salts varies, and the phosphate of soda which I employed gave me a wrong number for the atomic weight of phosphoric acid. End of section 66.
Section 67 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 7, of the Present State of Chemistry, Part 1. To finish this history, it will now be proper to lay before the reader a kind of map of the present state of chemistry, that he may be able to judge how much of the science has been already explored, and how much still remains untrodden ground. Leaving out of view light, heat, and electricity, respecting the nature of which only conjectures can be formed, we are at present acquainted with 53 simple bodies, which naturally divide themselves into 3 classes, namely, supporters, acidifiable bases, and alkalifiable bases. The supporters are oxygen, chlorine, bromine, iodine, and fluorine. They are all in a state of negative electricity, for when compounds containing them are decomposed by the voltaic battery, they all attach themselves to the positive pole. They have the property of uniting with every individual belonging to the other 2 classes. When they combine with the acidifiable bases in certain proportions, they constitute acids. When with the alkalifiable bases, alkalis. In certain proportions they constitute neutral bodies, which possess neither the properties of acids or alkalis. The acidifiable bases are 17 in number, namely, hydrogen, azote, carbon, boron, silicon, sulfur, selenium, tellurium, phosphorus, arsenic, antimony, chromium, uranium, molybdenum, tungsten, titanium, columbium. These bodies do not form acids with every supporter or in every proportion, but they constitute the bases of all the known acids, which form a numerous set of bodies, many of which are still imperfectly investigated. And indeed there are a good many of them that may be considered as unknown. These acidifiable bases are electropositive, but they differ in this respect considerably from each other, hydrogen and carbon being 2 of the most powerful, while titanium and columbium have the least energy. Sulfur and selenium, and probably some other bodies belonging to this class, are occasional electronegative bodies, as well as the supporters. Hence, when united to other acidifiable bases, they produce a new class of acids, analogous to those formed by the supporters. These have got the name of sulfur acids, selenium acids, etc. Sulfur forms acids with arsenic, antimony, molybdenum, and tungsten, and doubtless with several other bases. To distinguish such acids from alkaline bases, I have of late made an alteration in the termination of the old word sulphuret, employed to denote the combination of sulfur with a base. Thus, sulfide of arsenic means an acid formed by the union of sulfur and arsenic. Sulphuret of copper means an alkaline body formed by the union of sulfur and copper. The term sulfide implies an acid, the term sulphuret a base. This mode of naming has become necessary, as without it many of these new salts could not be described in an intelligible manner. The same mode will apply to the acid and alkaline compounds of selenium. Thus, a selenide is an acid compound, and a selenet an alkaline compound, into which selenium acts the part of a supporter or electronegative body. The same mode of naming might and doubtless will be extended to all the other similar compounds as soon as it becomes necessary. In order to form a systematic nomenclature, it will speedily be requisite to new model all the old names which denote acids and bases, because unless this is done, the names will become too numerous to be remembered. At present, we denote the alkaline bodies formed by the union of manganese and oxygen by the name of oxides of manganese, and the acid compound of oxygen in the same metal by the name of manganesic acid. The word oxide applies to every compound of a base and oxygen, whether neutral or alkaline, but when the compound has acid qualities, this is denoted by adding the syllable "ic" to the name of the base. This mode of naming answered tolerably well as long as the acids and alkalis were all combinations of oxygen with a base. But now that we know the existence of 8 or 10 classes of acids and alkalis, consisting of as many supporters or acidifiable bases united to bases, it is needless to remark how very defective it has become. But this is not the place to dwell longer upon such a subject. The alkalifiable bases are 31 in number, namely, potassium, sodium, lithium, barium, strontium, calcium, magnesium, aluminum, glucinum, yttrium, cerium, zirconium, thorium, iron, manganese, nickel, cobalt, zinc, cadmium, lead, tin, bismuth, copper, mercury, silver, gold, platinum, palladium, rhodium, iridium, osmium. The compounds which these bodies form with oxygen and the other supporters constitute all the alkaline bases, or the substances capable of neutralizing the acids. Some of the acidifiable bases, when united to a certain portion of oxygen, constitute not acids but bases or alkalis. Thus the green oxides of chromium and uranium are alkalis, while, on the other hand, there is a compound of oxygen and manganese which possesses acid properties. In such cases it is always the compound containing the least oxygen which is an alkali, and that containing the most oxygen that is an acid. The opinion at present universally adopted by chemists is, that the ultimate particles of bodies consist of atoms, incapable of further division, and these atoms are of a size almost infinitely small. It can be demonstrated that the size of an atom of lead does not amount to so much as 1/888,492,000,000,000th of a cubic inch. But, notwithstanding this extreme minuteness, each of these atoms possesses a peculiar weight and a peculiar bulk which distinguish it from the atoms of every other body. We cannot determine the absolute weight of any of them, but merely the relative weights, and this is done by ascertaining the relative proportions in which they unite. When two bodies unite in only one proportion, it is reasonable to conclude that the compound consists of one atom of the one body, united to one atom of the other. Thus, oxide of bismuth is a compound of 1 oxygen and 9 bismuth, and, as the bodies unite in no other proportion, we conclude that an atom of bismuth is 9 times as heavy as an atom of oxygen. It is in this way that the atomic weights of the simple bodies have been attempted to be determined. The following table exhibits these weights referred to oxygen as unity, and deducted from the best data at present in our possession. Oxygen, atomic weight 1. Fluorine, atomic weight 2.25. Chlorine, atomic weight 4.5. Bromine, atomic weight 10. Calcium, atomic weight 2.5. Magnesium, atomic weight 1.5. Aluminum, atomic weight 1.25. Glucinum, atomic weight 2.25. Iodine, atomic weight 15.75. Hydrogen, atomic weight 0.125. Azote, atomic weight 1.75. Carbon, atomic weight 0.75. Boron, atomic weight 1. Silicon, atomic weight 1. Phosphorus, atomic weight 2. Sulfur, atomic weight 2. Selenium, atomic weight 5. Tellurium, atomic weight 4. Arsenic, atomic weight 4.75. Antimony, atomic weight 8. Chromium, atomic weight 4. Uranium, atomic weight 26. Molybdenum, atomic weight 6. Tungsten, atomic weight 12.5. Titanium, atomic weight 3.25. Columbium, atomic weight 22.75. Potassium, atomic weight 5. Sodium, atomic weight 3. Lithium, atomic weight 0.75. Barium, atomic weight 8.5. Strontium, atomic weight 5.5. Yttrium, atomic weight 4.25. Zirconium, atomic weight 5. Thorium, atomic weight 7.5. Iron, atomic weight 3.5. Manganese, atomic weight 3.5. Nickel, atomic weight 3.25. Cobalt, atomic weight 3.25. Cerium, atomic weight 6.25. Zinc, atomic weight 4.25. Cadmium, atomic weight 7. Lead, atomic weight 13. Tin, atomic weight 7.25. Bismuth, atomic weight 9. Copper, atomic weight 4. Mercury, atomic weight 12.5. Silver, atomic weight 13.75. Gold, atomic weight 12.5. Platinum, atomic weight 12. Palladium, atomic weight 6.75. Rhodium, atomic weight 6.75. Iridium, atomic weight 12.25. Osmium, atomic weight 12.5. The atomic weights of these bodies, divided by their specific gravity, ought to give us the comparative size of the atoms. The following table, constructed in this way, exhibits the relative bulks of these atoms which belong to bodies whose specific gravity is known. Carbon, volume 1. Nickel and cobalt, volume 1.75. Manganese, copper, and iron, volume 2. Platinum and palladium, volume 2.6. Zinc, volume 2.75. Rhodium, tellurium, chromium, volume 3. Molybdenum, volume 3.25. Silica and titanium, volume 3.5. Cadmium, volume 3.75. Arsenic, phosphorus, and antimony, volume 4. Tungsten, bismuth, and mercury, volume 4.25. Tin and sulfur, volume 4.66. Selenium and lead, volume 5.4. Gold, silver, and osmium, volume 6. Oxygen, hydrogen, azote, and chlorine, volume 9.33. Uranium, volume 13.5. Columbium and sodium, volume 14. Bromine, volume 15.75. Iodine, volume 24. Potassium, volume 27. We have no data to enable us to determine the shape of these atoms. The most generally received opinion is that they are spheres or spheroids, though there are difficulties in the way of admitting such an opinion, in the present state of our knowledge, nearly insurmountable. The probability is that all the supporters have the property of uniting with all the bases, in at least 3 proportions. But by far the greater number of these compounds still remain unknown. The greatest progress had been made in our knowledge of the compounds of oxygen, but even there much remains to be investigated, owing in a great measure to the scarcity of several of the bases which prevent chemists from subjecting them to the requisite number of experiments. The compounds of chlorine have also been a good deal investigated, but bromine and iodine have been known for so short a time that chemists have not yet had leisure to contrive the requisite processes for causing them to unite with bases. The acids at present known amount to a very great number. The oxygen acids have been most investigated. They consist of 2 sets, those consisting of oxygen united to a single base, and those in which it is united to 2 or more bases. The last set are derived from the animal and vegetable kingdoms. It does not seem likely that the electrochemical theory of Davy applies to them. They must derive their acid qualities from some electric principle not yet adverted to, for, from Davy's experiments, there can be little doubt that they are electronegative as well as the other acids. The acid compounds of oxygen and a single base are about 32 in number. Their names are hyponitrous acid, nitrous acid, nitric acid, carbonic acid, oxalic acid, boracic acid, silicic acid, hypophosphorous acid, phosphorus acid, phosphoric acid, hyposulfurous acid, subsulfurous acid, sulfurous acid, sulfuric acid, hyposulfuric acid, selenious acid, selenic acid, arsenious acid, arsenic acid, antimonious acid, antimonic acid, oxide of tellurium, chromic acid, uranic acid, molybdic acid, tungstic acid, titanic acid, columbic acid, manganesic acid, chloric acid, bromide acid, iodic acid. The acids from vegetables and animal kingdoms, not reckoning a considerable number which consist of combinations of sulfuric acid with a vegetable or an animal body, amount to about 43. So at present we are acquainted with very nearly 80 acids which contain oxygen as an essential constituent. The other classes of acids have been but imperfectly investigated. Hydrogen enters into combination and forms powerful acids with all the supporters except oxygen. These have been called hydroacids. They are muriatic acid or hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrofluoric acid or fluoric acid, hydrosulfuric acid, hydroselenic acid, hydrotelluric acid. These constitute, such of them as can be procured, some of the most useful and most powerful chemical reagents in use. There is also another compound body, cyanogen, similar in its characteristics to a supporter. It also forms various acids by uniting to hydrogen, chlorine, oxygen, sulfur, etc. Thus we have hydrocyanic acid, chlorocyanic acid, cyanic acid, sulfocyanic acid, etc. We know also fluosilicic acid and fluoboric acids. If to these we add fulminic acid and the various sulfur acids already investigated, we may state without risk of any excess that the number of acids at present known to chemists and capable of uniting to bases exceeds 100. The number of alkaline bases is not perhaps so great, but it must even at present exceed 70, and it will certainly be much augmented when chemists turn their attention to the subject. Now every base is capable of uniting with almost every acid, in all probability in at least 3 different proportions, so that the number of salts which they are capable of forming cannot be fewer than 21,000. Now scarcely 1,000 of these are at present known, or have been investigated with tolerable precision. What a prodigious field of investigation remains to be traversed must be obvious to the most careless reader. In such a number of salts, how many remain unknown that might be applied to useful purposes, either in medicine, or as mordants, or dyes, etc.? How much, in all probability, will be added to the resources of mankind by such investigations need not be observed. End of section 67. Section 68 of the History of Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The History of Chemistry by Thomas Thomson. Volume 2, Chapter 7, of the Present State of Chemistry, Part 2. The animal and vegetable kingdoms present a still more tempting field of investigation. Animal and vegetable substances may be arranged under 3 classes: acids, alkalis, and neutrals. The class of acids presents many substances of great utility, either in the arts or for seasoning food. The alkalis contain almost all the powerful medicines that are drawn from the vegetable kingdom. The neutral bodies are important as articles of food, and are applied, too, to many other purposes of first-rate utility. All these bodies are composed, chiefly at least, of hydrogen, carbon, oxygen, and azote, substances easily procured abundantly at a cheap rate. Should chemists, in consequence of the knowledge acquired by future investigations, ever arrive at the knowledge of the mode of forming these principles from their elements at a cheap rate, the prodigious change which such a discovery would make upon the state of society must be at once evident. Mankind would be, in some measure, independent of climate and situation. Everything could be produced at pleasure in every part of the earth, and the inhabitants of the warmer regions would no longer be the exclusive possessors of comforts and conveniences to which those in less favored regions of the earth are strangers. Let the science advance for another century with the same rapidity that it has done during the last 50 years, and it will produce effects upon society of which the present race can form no adequate idea. Even already some of these effects are beginning to develop themselves. Our streets are now illuminated with gas drawn from the bowels of the earth, and the failure of the Greenland fishery during an unfortunate season like the last no longer fills us with dismay. What a change has been produced in the country by the introduction of steamboats, and what a still greater improvement is at present in progress when steam carriages and railroads are gradually taking the place of horses and common roads. Distances will soon be reduced to 1/2 of what they are at present, while the diminished force and increased rate of conveyance will contribute essentially to lower the rest of our manufactures, and enable us to enter into a successful competition with other nations. I must say a few words upon the application of chemistry to physiology before concluding this imperfect sketch of the present state of the science. The only functions of the living body upon which chemistry is calculated to throw light are the processes of digestion, assimilation, and secretion. The nervous system is regulated by laws seemingly quite unconnected with chemistry and mechanics, and in the present state of our knowledge, perfectly inscrutable. Even in the process of digestion, assimilation, and secretion, the nervous influence is important and essential. Hence, even of these functions, our notions are necessarily very imperfect, but the application of chemistry supplies us with some data at least, which are too important to be altogether neglected. The food of man consists of solids and liquids, and the quantity of each taken by different individuals is so various that no general average can be struck. I think that the drink will, in most cases, exceed the solid food in nearly the proportion of 4 to 3, but the solid food itself contains not less than 7/10 of its weight of water. In reality, then, the quantity of liquid taken into the stomach is to that of solid matter as 10 to 1. The food is introduced into the mouth, comminuted by the teeth, and mixed up with the saliva into a kind of pulp. The saliva is a liquid expressly secreted for this purpose, and the quantity certainly does not fall short of 10 ounces in the 24 hours. Indeed, I believe it exceeds that amount. It is a liquid almost as colorless as water, slightly viscid, and without taste or smell. It contains about 3/1000ths of its weight of a peculiar matter, which is transparent and soluble in water. It has suspended in it about 1.41 of its weight of mucus, and in solution about 2.81 of common salt and soda. The rest is water. From the mouth, the food passes into the stomach, where it is changed to a kind of pap called chyme. The nature of the food can readily be distinguished after mastication, but when converted into chyme it loses its characteristic properties. This conversion is produced by the action of the 8th pair of nerves, which are partly distributed on the stomach, for when they are cut the process is stopped. But if a current of electricity, by means of a small voltaic battery, be made to pass through the stomach, the process goes on as usual. Hence the process is obviously connected with the action of electricity. A current of electricity, by means of the nerves, seems to pass through the food in the stomach, and to decompose the common salt which is always mixed with the food. The muriatic acid is set at liberty and dissolves the food, for chyme seems to be simply a solution of the food in muriatic acid. The chyme passes through the pyloric orifice of the stomach into the duodenum, the first of the small intestines, where it is mixed with 2 liquids, the bile, secreted by the liver, and the pancreatic juice, secreted by the pancreas, and both discharged into the duodenum to assist in the further digestion of the food. The chyme is always acid, but after it has been mixed with the bile the acidity disappears. The characteristic constituent of the bile is a bitter-tasted substance called picromel, which has the property of combining with muriatic acid and forming with it an insoluble compound. The pancreatic juice also contains a peculiar matter to which chlorine communicates a red color. The use of the pancreatic juice is not understood. During the passage of the chyme through the small intestines it is gradually separated into 2 substances, the chyle, which is absorbed by the lacteals, and the excrementitious matter, which is gradually protruded along the great intestines and at last evacuated. The chyle, in animals that live on vegetable food, is semi-transparent, colorless, and without smell, but in those that use animal food is white, slightly similar to milk, with a tint of pink. When left exposed to the air it coagulates as blood does. The coagulum is fibrin. The liquid portion contains albumin and the usual salts that exist in the blood. Thus the chyle contains 2 of the constituents of blood, namely albumin, which perhaps may be formed in the stomach, and fibrin, which is formed in the small intestines. It still wants the 3rd constituent of blood, namely the red globules. From the lacteals the chyle passes into the thoracic duct, thence into the left subclavian vein, by which it is conveyed to the heart. From the heart it passes into the lungs, during its circulation through which the red globules are supposed to be formed, though of this we have no direct evidence. The lungs are the organs of breathing, a function so necessary to hot-blooded animals that it cannot be suspended even for a few minutes without occasioning death. In general, about 20 inspirations and as many expirations are made in a minute. The quantity of air which the lungs of an ordinary sized man can contain, when fully distended, is about 300 cubic inches. But the quantity actually drawn in and thrown out during ordinary inspirations and expirations amounts to about 16 cubic inches each time. In ordinary cases the volume of air is not so sensibly altered by respiration, but it undergoes two remarkable changes. A portion of its oxygen is converted into carbonic acid gas, and the air expired is saturated with humidity at the temperature of 98 degrees. The moisture thus given out amounts to about 7 ounces troy, or very little short of half an avoirdupois pound. The quantity of carbonic acid formed varies much in different individuals and also at different times in the day, being a maximum at 12 o'clock at noon and a minimum at midnight. Perhaps 4 of carbonic acid in every 100 cubic inches of air breathed may be a tolerable approach to the truth, that is to say that every 6 respirations produce 4 cubic inches of carbonic acid. This would amount to 19,200 cubic inches in 24 hours. Now the weight of 19,200 cubic inches of carbonic acid gas is 18.98 troy ounces, which contain rather more than 5 troy ounces of carbon. These alterations in the air are doubtless connected with corresponding alterations in the blood, though with this respect to the specific nature of these alterations we are ignorant. But there are two purposes which respiration answers, the nature of which we can understand, and which seem to afford a reason why it cannot be interrupted without death. It serves to develop the animal heat, which is so essential to the continuance of life, and it gives the blood the property of stimulating the heart, without which it would cease to contract, and put an end to the circulation of the blood. This stimulating property is connected with the scarlet color which the blood acquires during respiration, for when the scarlet color disappears the blood ceases to stimulate the heart. The temperature of the human body in a state of health is about 98 degrees in this country, but in the torrid zone it is a little higher. Now, as we are almost always surrounded by a medium colder than 98 degrees, it is obvious that the human body is constantly giving out heat, so that if it did not possess the power of generating heat, it is clear that its temperature would soon sink as low as that of the surrounding atmosphere. It is now generally understood that common combustion is nothing else than the union of oxygen gas with the burning body. The substances commonly employed as combustibles are composed chiefly of carbon and hydrogen. The heat evolved is proportional to the oxygen gas which unites with these bodies. And it has been ascertained that every 3 3/4 cubic inches of oxygen which combine with carbon or hydrogen occasion the evolution of 1 degree of heat. There are reasons for believing that not only carbon but also hydrogen unite with oxygen in the lungs, and that therefore both carbonic acid and water are formed in that organ. And from that late experiment of M. Dupré, it is clear that the heat evolved in a given time by a hot-blooded animal is very little short of the heat that would be evolved by the combustion of the same weight of carbon and hydrogen consumed during that time in the lungs. Hence it follows that the heat evolved in the lungs is the consequence of the union of the oxygen of the air with the carbon and hydrogen of the blood, and that the process is perfectly analogous to combustion. The specific heat of arterial blood is somewhat greater than that of venous blood. Hence the reason why the temperature of the lungs does not become higher by breathing, and why the temperature of the other parts of the body are kept up by the circulation. The blood seems to be completed in the kidneys. It consists essentially of albumin, fibrin, and the red globules, with a considerable quantity of water, holding in a solution certain salts which are found equally in all the animal fluids. It is employed during the circulation in supplying the waste of the system, and in being manufactured into all the different secretions necessary for the various functions of the living body. By these different applications, if we cannot doubt that its nature undergoes very great changes, and that it would soon become unfit for the purposes of the living body were there not an organ expressly destined to withdraw the redundant and useless portions of that liquid, and to restore it to the same state that it was when it left the lungs. These organs are the kidneys, through which all the blood passes, and during its circulation through which the urine is separated from it and withdrawn altogether from the body. These organs are as necessary for the continuance of life as the lungs themselves. Accordingly, when they are diseased or destroyed, death very speedily ensues. The quantity of urine voided daily is very various, though doubtless it bears a close relation to that of the drink. It is nearly but not quite equal to the amount of the drink, and it is seldom, in persons who enjoy health, less than 2 pounds avoirdupois in 24 hours. Urine is one of the most complex substances in the animal kingdom, containing a much greater number of ingredients than are to be found in the blood from which it is secreted. The water in urine voided daily amounts to about 1.866 pounds. The blood contains no acid except a little muriatic. But in urine we find sulfuric, phosphoric, and uric acids, and sometimes oxalic and nitric acids, and perhaps also some others. The quantity of sulfuric acid may be about 48 grains daily, containing 19 grains of sulfur; the phosphoric acid about 33 grains, containing about 14 grains of phosphorus; the uric acid may amount to 14 grains. These acids are in combination with potash or soda or ammonia, and also with a very little lime and magnesia. The common salt evacuated daily in the urine amounts to about 62 grains. The urea, a peculiar substance found only in the urine, amounts to perhaps as much as 420 grains. It would appear from these facts that the kidneys possess the property of converting the sulfur and phosphorus, which are known to exist in the blood, into acids, and likewise of forming other acids and urea. The quantity of water thrown out of the system by the urine and lungs is scarcely equal to the amount of liquid daily consumed along with the food. But there is another organ which has been ascertained to throw out likewise a considerable quantity of moisture. This organ is the skin, and the process is called perspiration. From the experiments of Lavoisier and Seguin, it appears that the quantity of moisture given out daily by the skin amounts to 54.89 ounces. This, added to the quantity evolved from the lungs and the urine, considerably exceeds the weight of liquid taken with the food, and leaves no doubt that water as well as carbonic acid must be formed in the lungs during respiration. Such is an imperfect sketch of the present state of that department of physiology which is most intimately connected with chemistry. It is amply sufficient, short as it is, to satisfy the most careless observer how little progress has hitherto been made in these investigations, and what an extensive field remains yet to be traversed by future observers. End of section 68. End of the History of Chemistry by Thomas Thomson.